Welcome to RSET Online lectures on the subject CS309 Graph Theory and Combinatorics for the semester. We know a Hamiltonian cycle visits every node of a graph exactly once. This is an example for Hamiltonian circuit starting from 1 along 2, 3, 4, 5, 6, etc. up to 20, passing through all the vertices exactly once and return to 1. And a complete graph is defined as a simple graph in which there exists an edge between every pair of vertices. This is an example for two vertices. The complete graph is denoted as K2, complete graph with the three vertices K3, complete graph with four vertices K4, and this is complete graph with five vertices. A complete graph is sometimes also referred to as universal graph or a clique. A complete graph with n vertices is denoted as Kn. Next, we can explain a theorem related to complete graph. A complete graph with n vertices, then there exists n minus 1 divided by 2 edge-disjoint Hamiltonian circuits. If n is an odd number greater than or equal to 3. You can see the proof. A complete graph G of n vertices has n into n minus 1 by 2 edges. Since the degree of each vertex in a complete graph G is n minus 1, by first theorem of graph theory, the sum of degrees of vertices is equal to 2 into E. Since each vertex is of degree n minus 1, then sum of degrees of vertices equal to n into n minus 1. That is equal to 2e, and therefore total number of edges in G is given by E is equal to n into n minus 1 by 2. A Hamiltonian circuit in G consists of n edges with n vertices. Therefore, the number of edge-disjoint Hamiltonian circuits in G cannot exceed n minus 1 by 2. And here we have to prove that there are exactly n minus 1 by 2 edge-disjoint Hamiltonian circuits if n is an odd number greater than or equal to 3. We can explain this using an example. Assume that this is a graph with 9 vertices. Starting from 1, we can move along this edge to 2, then 3, 4, 5, 6, 7, 8, 9, then return to 1. This is one Hamiltonian circuit. We can define another set of Hamiltonian circuit like this. That means we are keeping the vertex 1 fixed and the remaining vertices around the circle, so that keeping the vertex fixed on the circle and rotate the polygon pattern clockwise by 1 into 2 pi divided by 9 minus 1, that is 8, where 9 is the number of vertices in the graph. Then that means you are rotating the polygon by pi by 4, angle pi by 4. Then this 5 will come to this position, that is denoted by the letter in green. The 7 will come to this position, that is in the second position. We are denoted it as green letter. Then this 9 will come to this position like that. 8 will come to this one. The 6 will come to this position. And 4 will come to this position like that. 2 will come to this position. Now, in the second line, we can define the next Hamiltonian circuit like this. Starting from 1, along this edge, coming to 4, then 2, then 6, 3, 8, 5, 9, 7 and return to 1. And this Hamiltonian circuit starting from 1 ending by 1 along another set of edges. The first one and second Hamiltonian circuit have no edge in common. Like that, if with this position, if we are rotating again by angle pi by 4, that is 2 times 2 pi by 8 from the starting point, then this 3 will come to this position, that is denoted in red letter. This 5 will come to this position and 7 will come to this position denoted by 7. Like that, we can fix all the numbers, all the vertices in the polygon. Then next Hamiltonian circuit can be defined like this: 1 to 6, the red letter, then 6 to 4, 4 to 8, 8 to 2, 2 to 9, 9 to 3, 3 to 7, 7 to 5, then along the sets 5 to 1. That gives the third Hamiltonian circuit. Again, rotate this polygon by pi by 4 from that position, that is 3 into 2 pi by 8 from the original position. You will get similarly the next Hamiltonian circuit as 1 to 8, this blue letter, 8 to 6, 6 to 9, 9 to 4, 4 to 7, 7 to 2, 2 to 5, 5 to 3, then 3 to 1. That gives the fourth Hamiltonian circuit. That means you are getting 4 distinct Hamiltonian circuits in which no edges are common. Now, if we are again rotating by pi by 4, you will get the next Hamiltonian circuit as like this: 1 to 9, 9 to 8, 8 to 7, 7 to 6, 5, then 4, 3, 2, then back to 1. See, the first and last Hamiltonian circuit, that is in the reverse order: 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. But both are same. That means you are getting, if there are 9 or vertices in a complete graph, you can find exactly 4 edge-disjoint Hamiltonian circuit. That is n minus 1 divided by 2, where n equal to 9. 9 minus 1 by 2 is equal to 4. You can generalize. The graph G shown in the following figure is a Hamiltonian circuit. Similarly, if there are n vertices and suppose n is an odd number, we can fix 1 here and the remaining vertices 2, 3, 4, 5, 6, etc. On the circle and rotate. Keeping the vertex fixed on the circle, rotate the polygon pattern clockwise by 2 pi by n minus 1, 2 into 2 pi by n minus 1, etc. n minus 3 by 2 into 2 pi by n minus 1 degrees. Each rotation produces a Hamiltonian circuit that has no edges in common with any of the previous one. If we are counting this, we get 1, 2, 3, etc. n minus 3 by 2 plus the original Hamiltonian circuit, the beginning Hamiltonian circuit in the order 1, 2, 3, etc. n back to 1. That gives total n minus 1 by 2 distinct edge-disjoint Hamiltonian circuits. Hence the theorem. This is end of part 3. Thank you.